Hey everyone, welcome back to Calculus 2. In this lecture, we're going to get into area. This will be the second lecture of the course. We're going to get into a discussion of area, and specifically we're going to be looking into the problem of finding the area of a region in the plane, obviously in the plane, but specifically finding the area under an arbitrary curve in the plane. Okay, so it'll be a little bit of work to get there, but we're going to build up to it, and then in the coming sections we'll be connecting this idea of area that we'll develop here. We'll be connecting it to what's called the definite integral and integration more generally. So let's go ahead and get started. We'll call this section 1.2 and just area. Okay, so to start with, we're going to need some mathematical notation that is maybe some are familiar with who are watching this, but if you are truly taking Calculus 2 for the first time, this will be probably new. And that's going to be the sigma notation. Okay, so this is called the sigma notation. And it's a convenience that's used in mathematics to denote sums of quantities. So here's what we would say: the sum of n terms, and we'll just say A1, A2, all the way up to AN, okay, can be written as, okay, big sigma, that's like a capital sigma, large sigma, Greek letter, and then we usually have an I equals 1 up to n. In this case, the indexes range from 1 up to n, and so the sigma notation would say the sum of something from I equals 1 up to n, and the something in this case would be denoted as AI, A sub I. And that's literally just equal to A of 1 plus A of 2 plus, and so on, all the way up to A of n. Okay, and so when we're dealing with sums of a large number of terms, or even potentially an infinite number of terms, this notation is invaluable. Okay, and so it will be an absolute necessity pretty much for the rest of Calculus 2. So let's do some examples and make sure we understand this concept. So we'll start simple. Sum of I from 1 up to 6, we'll say. Okay, so in this case, the term itself is I, and we would sub in 1 up to 6. So it'd be like 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, so like the sum from I equals 1 up to 6. And of course you can add those together and get 21. Okay, the indices can vary. So, it's maybe typical to start at I equals 1, but you wouldn't have to, right? So you could say I equals 0 up to 5 of I plus 1, right? And in this case, you would get the same sum, right? The I equals 0 term would be 0 plus 1 is 1, and then plus the I equals 1 term would be 1 plus 1 is 2, right? And the fifth term, well, I guess the sixth term technically here, but the I equals 5 would be 5 plus 1 equals 6. So as you can see, it go all the way up to 6, just like in the previous example. Okay, so there's different ways to write what is essentially the same sum. Now these terms that you're summing can be as complicated as you like. So here's another example. And it's maybe most common to use I as the indexing variable, but you'll see K very frequently as well. So what if we want the sum from, as K goes from 1 up to N, of, and now n is just an arbitrary number that you can plug in, you could evaluate to different values. But let's say the term itself is 1 over n times k squared plus 1. Right, so in this case, every term is going to be divided by n, whatever n happens to be, and then this piece of the sum is what's going to increase term by term. Okay, so for example, you would get 1 over n times 1 squared plus 1 plus 1 over n times, when k equals 2, this would be 2 squared plus 1, and so on all the way up to 1 over n times n squared plus 1. Okay. Now, one thing you'll notice here is that since every term has a 1 over n factor, you can factor that out of the sum. So you could write it just like this. Right, so you could write it like this. Looks good. And of course, that kind of implies that the sum itself could be written like this. Right, so i.e. you could factor out any constant any constant from the expression, like right off the bat. You wouldn't have to expand it. Okay, so that's an example, and we'll get into a few properties that are going to be important with this sigma notation in a moment. Let's take a slightly more abstract example. What about this? The sum as I goes from 1 up to n of some function evaluated at some value xi times some other value called delta x. Okay, now this sum will be used extensively later in the lecture. But you can see that, so this is some arbitrary function, we don't know what it is, but the sum is going to work the same. It'll be f evaluated at x1 times delta x plus f evaluated at x2 times delta x plus all the way, and so on, up to f evaluated at the last term in the sequence xn times delta x. Okay. And then of course you could, delta x being common to every term, you could factor it out like so. Right, and then you would just have the sum itself, and then I guess, it would be prudent at the beginning to factor it out as well. Like so. Okay. So these are just some examples. This notation is something this is a staple of mathematics from basically here on out. You'll use this in, I can't imagine a math class that wouldn't leverage sigma notation from Calculus 2 onward. So yeah, it's a good one to make sure you're comfortable with. This is just an introduction to it, and we'll be using it throughout the lecture and really throughout the rest of the course, so you'll get comfortable with it pretty quickly. It's pretty intuitive notation. Okay, so there it is. That's the sigma notation. Now there's a couple of properties that we're going to need, and some identities for sigma notation. And so a couple of properties. Okay, so the first one is the one that we've already kind of seen. If I have some sum I equals 1 to n, we'll say, and there's a constant k times some expression ai, then I can factor the constant out of the sum, which means you can pull it out of the notation, like so. Right, and this is the example we've seen with, first we saw the 1 over n example, and then the last example was the delta x example, right? So we've seen this one. Okay, so that one's pretty intuitive. We really just have to expand it to kind of see. The second one is the sum of, so I equals 1 up to n. Now here, each of the terms is has a sum or difference in it. So AI plus or minus a BI. Okay. And so in this case, it's appropriate to break the sum of each term apart, like so. Okay, like so. Now, this can be really easily seen. Let's see. So let's just take a small example to show how this would work. I equals 1 to 3, we'll say, of AI plus BI. It works the same for differences, really. So this would be A1 plus B1 plus A2 plus B2 plus A3 plus B3. Right? That's just expanding the notation out to the actual sum. And then you can rearrange these, right? This is all just addition. So this can all be rearranged until you get A1. You can arrange it as such. A1 plus A2 plus A3 plus B1 plus B2 plus B3. Right, then of course you can group these like that. And that's what leads directly to the I equals 1 to 3 AI plus I equals 1 to 3 BI. Right, so a really simple thing to see this, and hopefully intuitive. Both of these should be intuitive because we'll be using this extensively, and so we really want to make sure that these are intuitive. Okay. Now, I know it can be a little, I mean, if this is truly the first time you're seeing this, this can be a little like cumbersome, seemingly like, oh no, like a special Greek note, symbol for sums. Oh, this is getting, I know. I remember being in Calculus 2 and starting to think like, uh-oh, what have I gotten myself into here? But it is, you'll find that it is great convenience ultimately, and worth a little bit of a struggle at the beginning perhaps. So here's a theorem. We won't prove this. I think people can prove this on their own probably, and it's something that is sort of it's a side note for most of the stuff we're going to use, but it would be instructive to spend a little time on your own kind of working through some of these. Some of them are totally obvious. But this is basically going to be a collection of sums that are very useful and very common. So the first one is the sum of I equals 1 to n of some constant. Right? Like maybe C is the number 100. If I add 100 to itself n times, what do I get? Well, not surprisingly, you get whatever C is times n. Right, so C times n. So if C is the number 1, right, and I add 1 to itself n times, then I get 1 times n naturally, right? So the answer would be n. If C is 100, then it would be 100 plus 100 plus 100 n times whatever n happens to be, and you would get n times 100 or 100 times n. Okay, so really straightforward, that one. I think any of you could prove this one. It's just a matter of expanding the sum and grouping things, doing a factorization, I think, basically. Okay, then the next one would be this guy, I equals 1 to n of just I. Okay, and now this one turns out to be n times n plus 1 over 2. Okay, and so clearly in both cases, the sum can be calculated directly, but you just need to know, of course, what n is in order to figure out precisely what number the sum is equal to. Right? So here it's just in general, whatever n happens to be, you multiply it times n plus 1 and divide the whole thing by 2, and that's your sum. The third one is sum of I equals 1 to n of I squared. And for this guy, you get n times n plus 1 times 2n plus 1. Miraculous how this happens, all divided by 6. Okay. And then the last one that we'll need is I cubed. And there are many of these actually that you could go and reference. But if you are cubing a number and successively summing them, you would get n squared times n plus 1 squared over 4. So let's do like a very quick example here of each of these. So we'll just put a little example off to the side for each of these. So the sum of I equals 1 to 10 of 100. Well, that's just 100 times 10, right? So I guess that's 1,000. Okay. Now remember, this is just 100 plus 100 plus 100 10 times, right? So clear. What about, for an example here, let's go I equals 1 to 20 of I. And so what this would say is that it's equal to n times n plus 1. So n is 20 in our example. And all divided by 2. So this would be 20 times 21 over 2. And of course you could multiply that together, and figure out what that is. Well, I guess it's obvious that it's 210. Okay, so 210. Okay. So 1 plus 2 plus 3 plus 4 ... plus 20 is 210. You can confirm that. And so this is just a nice formula to get you to that finish line really quickly. How about down here, we'll go I equals 1 to 10 of I squared, just so we can plug these numbers in to see what it looks like, see how we evaluate these. This would be 10 times 10 plus 1 times 2 times 10 plus 1, all over 6. So that would be what? 10, and then 11, and then 21, all over 6. And I'll just leave that to you guys to figure out, but it's like 210 times 11, so like 2,000 something. And you could figure this out, just plug it in. And then down here, finally, let's go I equals 1 to, let's get crazy and say 15 of I cubed, right? So notice here, in every case, I squared, I cubed, these are the numbers that are just increasing: 1 cubed, 2 cubed, 3 cubed. And so here it'd be 15 squared times 15 plus 1 squared over 4. Again, you can figure that out. 15 squared times 16 squared over 4. Okay. All right. Very good. So that's sigma notation. Let's do a trickier one. Now, these really become valuable when you have more complicated expressions. So, for example, let's evaluate sum as from I equals 1 up to n of I plus 1 over n squared. Let's evaluate this for a couple of different values of n. So let's start with n equals 10. So that's simply I equals 1 to 10. Okay, now actually before we do this, what can we do with this sum? Right? We can actually rewrite this as 1 over n squared times the sum of I equals 1 to n of I plus 1, like so. And then further, we can break this into two sums, right? Because you've got I and then you've got plus 1. So this can also be written a little bit further on as 1 over n squared times, and now you can write the sum of I equals 1 to n of I plus the sum as from I equals 1 to n of just 1. Now, what's the advantage in doing it this way? Well, that theorem we just had, that we just looked at, tells us what this sum is equal to and tells us what this sum is equal to. Right? So we can use that theorem to figure out what the sum is equal to. right, for different values of 10. So just writing it out here again, okay, this could be written as 1 over n squared, and then its sum is I goes from 1 up to 10 of I plus I equals 1 to 10 of 1. Okay, and so that would be, technically we know what n is, so I should have written 1 over 10 squared here. And then what's the I? What is the sum from I equals 1 to 10 of I equal? Well, you could just reference the previous theorem and see that it's this. And then this one would be 10 times 1, so just 10. Okay, so we can crunch all those numbers. I've done this in advance, and so I can tell you that this is equal to 0.65. All right. What about n equals 100? Well, for n equals 100, so the sum is going to have this same form in each case. So the sum will be 1 over n squared, and then I equals 1 to n of I plus I equals 1 to n of 1, which we know is 1 over n squared, and then it's n plus 1 over 2 plus just n in this case, since you're adding 1 to itself successively. And so for n equals 100, the sum will equal 1 over 100 squared times 100 times 100 plus 1 over 2 plus 100. Right, that's what it'll look like. Okay, just following literally the same rules as before, but instead of plugging in 10s, we're plugging in 100s, right? Because the only thing that's changed from here to here is n equals 100 now. And so when we do that, the sum, I did this ahead of time, is 0.515. And you can just pause the video and verify that, yes, indeed, that is 0.515. What about like a much larger n? What about n equals 10,000? Certainly wouldn't want to try to solve this, either of these examples, using actual sums, right? Like i.e. 1 plus 2 plus 3 all the way up to 10,000. But very simple to do, relatively easy to do when you kind of follow the formula here. So in this case, the sum is equal to 1 over 10,000 squared, okay, and times 10,000 times 10,000 plus 1, all divided by 2, plus 10,000. Okay, and when you get this one, when you crank these numbers out, you get 0.50015. Okay, and so interesting, like, you can see that the values, as n increases very dramatically, the values of the sum do not change dramatically, well, relatively speaking, but it kind of looks like these sums maybe possibly could be converging to 0.5. Do these converge to 0.5? Well, indeed they do. It can be shown that the sum is 1/2 as n goes to infinity, right? It gets closer and closer to 1/2 as n goes to infinity. Now, the way we would write that is we would say that the limit as n approaches infinity of n plus 3 divided by n squared. Wait, hold on a second. N plus 1, I'm sorry. N plus 1 over n squared is 1/2. Okay? Okay. Actually, I'm wrong here. Miswrote that. So this one is actually limit as n goes to infinity of n plus 3 over 2n, n plus 1 over 2n. and that's 1/2. Okay, so at any rate, we're not totally ready for that yet, but the point is here that there's an enormous efficiency gain, in using this notation, and especially in using these sort of close-formed expressions, formulas for these really nice and common sums. Okay, all right, very good. Okay, so that's sort of the approach. Well, that's sort of the wind-up for what we're going to be talking about next. That's one of the wind-ups. There's actually a couple, right? So the first one is this summation notation, the sigma notation. Now, the second one is we want to start to kind of think conceptually about areas. Okay, so consider some area formulas. Okay, so for example, the one that everybody knows, the area of a rectangle. You've got a base, width, right? Meaning the width here, and you've got a height, right? And then the area here is the base times the height, right? So the amount of stuff inside the rectangle can be calculated as the amount of stuff in this dimension times the amount of stuff in that dimension, and that'll tell you the amount of stuff in the entire space. And so similarly for like triangles, let's say we've got a triangle that looks like this, and there's a height specified for the triangle and also a base. Okay, if that happens to be the case, then you can easily calculate that the area is equal to 1/2 the base times the height. Okay, so these are the kinds of figures that we're used to calculating the area of up until now, right? And what about the area of a circle? I know we all know that we have area equals pi r squared for the circle, right? So that's the area formula that everybody knows. But let's think about finding the area of a circle in a different way. So let me see if I can draw a decent circle here. And we're going to start with just an approximation game. So you've got the center of the circle. There's a method for finding the area and the method is called the exhaustion method. The exhaustion method for finding the area of a circular region. Okay, so what we would do is we'd say, okay, let's break the circle up into by drawing diameters at different angles to one another. And you can think of these as each being a triangle, like so. Right, now if I were to calculate the area of each one of these, or even just one of them, say that one, and then I multiply whatever this area happens to be times 1, 2, 3, 4, 5, 6, 7, 8, then that gives me a reasonable approximation to what the area of the circle would truly be. Now, the reason it's called the method of exhaustion is because, you can increase the number. Oh, that's really bad. Let me start with the circle and then draw the. Okay, so let's say we start with a circle, and we, instead of using 8 sections, we use more like 16. Then what happens? Now again, if you drew this really precisely with, like a compass, it would give you a better sense for this. But I think people can use their imaginations to understand what's going on here. So in the case of 16 rays, you get an area that more closely hugs the edge of the circle. You see there's a fair amount of missed area there, right? Now, as the rays get ever increasingly tighter, then the area between the actual arc of the circle and the edge of the triangle is going to decrease, right? And so obviously if we were to double it even further, what you would see is that the area that's missed, the area that's outside the triangle but yet inside the circle, gets even smaller, right? So basically it kind of comes up like that. And so if you think of this as the edge of the circle, okay, let's say we've got the intersection like this. We don't care what's happening up top here, but right, so you can see you've got that piece there. Well, if I were to have that, then right, the missed area decreases each time, right? So that's the idea with the area of the method of exhaustion for finding the area of a circular region, is to sort of take a shape that we know and are comfortable finding the area of, namely a triangle, and just start systematically setting up triangles inside of a circle, and then just increase the number of triangles until the discrepancy between what the area that is captured by the triangles and the area that's captured by the circle is arbitrarily small, right? So just let the number of triangles grow and grow and grow until you're comfortable that you're close enough to the actual value of the area of the circle. Now, theoretically speaking, the number of triangles that would be necessary to precisely equal the area of the circle would be what? I mean, to precisely equal the area of the circle, the number of triangles would have to be infinite, right? And that's sort of the fundamental idea here of the method of exhaustion, and that's what's going to translate into our area discussion. Okay, and so this same kind of argument can be made for just kind of any sort of region under a curve in the plane. So let's imagine that here's your xy coordinate, and let's imagine that we've got some function kind of decreasing like this, and let's say that we're interested in the area between these 2 points. Well, one way to do this would be to kind of break this space up into a certain interval and to draw rectangles underneath of it, like so. Right? And then to find the area of each rectangle. Right? So if I find the area of this rectangle, and I find the area of this rectangle, and so on, and I add all of those areas up, well, then that's going to get me, an estimate for the area between these 2 points underneath this curve. Now, let's say I double the size of the area, double or halve the width of the intervals. Then I'm going to capture more of the area, aren't I? So now I come all the way up like that. And you can see that the estimate gets better the more rectangles you have. And naturally, we could have them all again. Right? And when we do that, we cut out even more of the gap. Right? So you can imagine this getting as clean and hugging the curve as tightly as you want, right? And so clearly, if I had an infinite number of rectangles under here, the area would be precisely identical to the curve, right? Right. We're talking about the area all the way down to the x-axis here between A and B. Okay. So this is the same idea as what we saw with the circle. It's just here we're using rectangles. Here we're using triangles. And here we'd use rectangles, right, to approximate our area. Okay. All right, so that's sort of the background idea, right? That's kind of the background idea of finding the area using the method of exhaustion. Okay, let's explore this a little bit more. Now, in the previous example we just did, I used rectangles that were drawn under the curve, right? So they came up to the curve on the right-hand side and consequently created a gap under the curve, right? So let's just recreate that quick. So I have a curve here, and I want these curves to be kind of the same. Okay, so that looks pretty good. So let's say we have 2, 4, 6, 8, 2, 4, 6, 8. So over here, this is kind of how I drew it in the previous example. Right, so the right-hand side of the rectangle comes up, touches the curve, and when you do it this way, you end up with, your area is a little too small, isn't it? Right, the area is a little too small this way. Right, you can see the gap between the curve and the area being estimated using your rectangles. So another way to do it would be to use the so here we use the right hand side of the rectangle to identify the height, but what if we use the left hand side instead? So then you would end up with something like this. So go like that. Right, you see how we're kind of identifying the height of the rectangle based on where it touches the curve on the left-hand side. So here you end up with too much, right? Okay, so over here you have a gap, too little. And over here you have a surplus, too much. Okay, so which way is the right way? Well, as we'll see, there is these both are appropriate. So let's put some numbers on here. 1, 2, 3, 4. Okay, so let's say actually I'm gonna draw a new picture. We'll draw a new picture. So the difference here is that here we're using the left-hand side to identify the height, and here we use the right-hand side to identify the height. Okay. Okay, let's draw another picture here and see what this I want it to be kind of similar here. So we're gonna have 1, 2, 3, 1, 2, 3, 4, 5. So I'm gonna put some numbers on here. This will be 2/5, 4/5, 6/5, 8/5, 10/5. Okay, so this goes from basically 0 up to 2. Okay, and we'll put the same curve on there. Okay, now here we've got our rectangles underneath, and we'll just draw it like this. Okay, now in this example, the width of the rectangles is all the same, right? And so 5 intervals are created: 1, 2, 3, 4, 5. So 5 intervals, each of identical width. Okay, and really you could think of the intervals as being basically 0 up to 2/5, and then 2/5 up to 4/5, and then 4/5 up to 6/5, 6/5 to 8/5, and 8/5 up to 10/5. Okay, perfect. Okay, now obviously the width of each interval is 2/5. Okay, now where did the two, so the entire stretch is 0 up to 2. Okay, so the entire width of the width of the whole interval is 0 up to 2, and we have 5 intervals, so the width is basically 1. That's basically the width of the entire interval, 2 divided by the number of intervals. So the overall width divided by the number of intervals. Okay, this is I'm kind of taking my time and making sure that this construction is clear and kind of pointing out some of the key little pieces here. Now, how would we figure out what the height of each rectangle? So obviously the width is 2/5 for each of these, right? We can see that, right? You could subtract any of these two numbers and clearly get 2/5. Okay, so but how do we know what the height of the thing is, of the rectangle? Well, there's a function, right? So this is some kind of a function. In this case, the function I've actually drawn here is negative x squared plus 5. That's the name of it. That's the actual function. So what's the height of this thing? Well, the height can be identified by evaluating one of the endpoints, either the left-hand or the right-hand side, inside the function. So, for example, the height of the first interval is, well, if you use the right-hand side, you would get f of, what, 2/5, right? Which would be negative 2/5 squared plus 5, whatever that happens to be. If you use the left-hand side, right, the left-hand side of this first interval is 0. So you'd identify it as f of 0, right? So that'd be negative 0 squared plus 5. Well, that one is easy to do, 5. So this would be negative 4/25 plus 5. So that's negative 4 plus 25 over 25. Wait, hold on. No. That's totally wrong. Well, you could figure that out. Sorry about that. So you can figure that out just by cranking that through a calculator. But so the height of the interval is figured out. It can be identified by using the function itself evaluated at either this endpoint or that endpoint. Okay, so that's kind of going through like sort of how would we figure out what the dimensions of the rectangle are in order to multiply them together to calculate the area. Okay, so there's that. And so let's talk through what this sum would actually be. Okay, so in each case, let me bring this back. And let's just use the right-hand side. Okay, so using the right-hand side, well, the width of the triangle, of the rectangle, is 2/5. We've got that one figured out cold. Now, what's a formula for the right-hand side here? Right? What could I add together to get, what expression could be used to capture this one, this one, this one, this one, and this one, right, in that order? Well, what if I consider 2i consider 2i over 5. Okay, now this is always kind of a tricky part for people. So if I is equal to 1, then 2i over 5 is 2/5. If I is equal to 2, then 2i over 5 is equal to 4/5. If I is equal to 3, 2i over 5 is 6/5, right? I equals 4, I equals 5, 2i over 5, 2i over 5, right? In each case, you're going to get 8/5. 2 times 4 is 8, divided by 5 is 5, and then 10/5, right? Okay, so these are the exact intervals that we want. This is the indexing scheme that is convenient. So consider 2i over 5 as a as an index for the argument to calculate the height. Okay, so the height, right, the width is always the same. It's always 2/5. The height is going to vary, but it's always going to be the function evaluated at 2i over 5 for I equals 1, 2, all the way up to 5. Okay? Okay, so the width is always 2/5. That's fine. The height is going to be the function evaluated at 2/5, then the function evaluated at 4/5, 6/5, 8/5, 10/5. A convenient way to write this is to write f of 2i over 5 for I equals 1, 2, 3, 4, 5. Okay. So can we calculate this area? Indeed, we can. The area, then, is going to be the sum from I equals 1 up to 5 of the height times the width. Right, I'll just write that first. Height at I times the width at I. Okay, so that's I equals 1 up to 5. Now the height is right here. So it'll be f of 2i over 5. And the width, well, the width is a constant. It's always 2/5. Irregardless of which interval you're looking at, they're always the same. So this is good. We're getting somewhere. Okay. Now, f of 2i over 5. Now remember the function f of x was equal to negative x squared plus 5. So we have to kind of remember that. That's the actual function. So this would be equal to the sum from I equals 1 up to 5 of negative 2i over 5 squared. Right? This is the x squared with the 2i over 5 in there. That's what we're evaluating, remember, f of 2i over 5. And then plus 5. Don't forget the plus 5 there. Okay, so that thing there times 2/5. Okay, so this is our sum. Okay, and well, this is kind of a mess, isn't it? There are things we could do here to simplify this, right? But you know, you could, for example, pull the 2/5 out. You could pull the negative 2/5. No, we can't do that. So it'd be negative 2i over 5 squared plus 5. Right, you could break this into two pieces, and then you could pull the negative 2/5 out. I'll just kind of go through it, actually. So you've got the 2/5. And then you can break this into two sums in here. I equals 1 to 5 of negative 2i over 5 squared plus the sum I equals 1 to 5 of 5. Okay, we can do that. And then this could be cleaned up in here. And you could pull out the 2/5 squared, so it'd be negative 4/25. And then the sum from I equals 1 to 5 of I squared plus the sum I equals 1 to 5 of 5. Okay, and I think you're probably seeing, hey, here's the sum of I squared, here's the sum of a constant, and so we could get all of these values out here. Negative 4 over 25, and then what is this? I think if we recall, this was n plus 1 over 2, correct? Yep. So this would be 5 plus 1 over 2. That's this one. And then plus what? Well, 5 times 5 plus 25. Okay, and so then you could, now everything is just a number. You could easily calculate this. And if you do this, you end up with 6.48. So confirm that. pause the video, confirm that that's the case. And so the the area calculated in this way would be approximately 6.48, right? Now remember, this is using the right hand side as the height. Okay. What happens if we use the left hand side as the height? Well, we're naturally going to get a different answer, right? So if you recall, the right hand side would produce an area smaller than actual. Okay, the left hand side should produce an area that's larger than actual, and that's specific to this function because this function is decreasing on the interval 0 to 2. But if we do the sum based on the left hand side, okay, if we do the sum based on the left-hand side, then our sum would be I equals 1 to 5. And now, what's the height here? Well, the height turns out to be somewhat different. And I'll just write it and let you guys confirm / unwind it. It looks like this. So each of the each of the arguments that you plug in is 2i over 5 minus 2/5. Okay, now that might be something. So before it was 2i over 5, right? That would get you this endpoint, this endpoint, this endpoint. Now it's 2i over 5 minus 2/5, right? 2i over 5 gets us here, and if we want the other interval, we have to subtract 2/5. So that would get you this side. Okay, so hopefully that's basically the same derivation, just minus 2/5, just kind of scooch it over a bit. Okay, so you'd have, this is the height, and then the width is always 2/5, so it's the same as the previous. Right, remember, all we're doing here is we're calculating area of rectangles, but we're trying to set it up in this sort of concise sum. And then if we could plug in each of the, we could, actually plug in the proper terms here. So remember, the function is negative x squared plus 5. Oh, plus 5. Okay. And so this would become negative 2i over 5 minus 2/5 squared plus 5 times 2/5. Okay, and just like in the previous example, you could go through and figure out what this sum amounts to. You would have to. It's a little more complicated. You'd have to square this term and then collect terms and then distribute the 2/5 across everything. And what you'd end up with is something that looks a little bit like a polynomial with some rational coefficients, and you could factor it all out. But I think you'd have an I squared term in there, and then you'd have an I term, and then a constant, basically. And so when you did all of that, there'd be a fair amount to do, and I'm going to kind of skip it in the interest of time. But what you'd end up with, and I did this off to the side, you'd end up with something like 8.08 approximately. Okay, so you would get approximately 8.08. And now remember, this is an approximation. Is it going to be a low or high approximation? This one would be too high, right? I mean, we're only using 5 rectangles, so it's definitely not going to be precise, right? But so before we had 6.48, we had 6.48 as our area using right-hand side. And now we have 8.08 as the area using the left-hand side. Now, the true area is somewhere between those two values, right? Somewhere between those two values. Okay. Now, as you kind of can guess, right, as we increase the number of rectangles, then this interval would go from being very wide to less wide to less wide to less wide to less wide, until eventually it could be as small as you like, right? So you're arbitrarily larger or arbitrarily smaller than the true area. Okay, so that's kind of the starting example. Right now, we sort of set all of that up using a very specific example. And now what we want to do next, next, what we'll do is generalize this. We're going to generalize the process. I'm going to break this lecture up into two parts, just simply due to the length. So we'll stop here, and when we come back, we are going to be generalizing the process that we just laid out.